In this video, we're going to cover the properties of definite integrals that appear on page 511 in your notes. And it also appears, these rules also basically appear in the integrals reference sheet that I have linked on Schoology. So you can see it in either one of those places, but I wanted to take a little bit of time to give you a chance to kind of understand where these rules come from and maybe internalize them in your brain a little bit. The instructions they have here are to look at the rules and see if you can guess what they are just from the left-hand sides of the equation. In some of those, that's easier than other times, but give it a good shot for a minute or two and see what you get, and then we will go through them together as a group right now. Okay. So let's take a look. The first rule says that we have the integral from a to a of f of x dx. So the left and right bounds of the integral are the same. So we might imagine a function, that looks like this, and there's our x-axis, and we're only interested in a single point A. All right, so we've been talking about the area of a rectangle, but what's the area of that line, do you think? Right there where x is equal to a. And the answer is 0. Lines don't have any area. And the integral of something from one point to itself is just going to be 0 by definition, because there's no area that's swept out by that. The second rule here says that given that a is less than c, which is less than b, the definite integral from a to b of f of x dx. So here it's not 100% clear what they're looking at, but again, we'll consider some function here. And here's our a, and here's our b. And let's say that there's some c in the middle of it. All right, so is there some way that we can involve c in this expression? Well, this definite integral is the interval of this entire shape from a to b. So what they're getting at there is that this is equal to the definite integral from a to c plus the definite integral from c to b of the same thing. So we can break up a definite integral into two pieces. Okay, the next thing here says that if the definite integral from a to b of f of x dx is equal to k, did you notice how this one is a little bit different? Take a closer look if you didn't notice. This is the definite integral from b to a of f of x dx. All right, so remember our fundamental theorem of calculus that says that if big F is an antiderivative, then the definite integral from a to b of f of x dx is equal to big F of b minus big F of a. And so if we wanted to think about the integral from b to a of the same thing, that would be pretty much the same thing, except it would be f of a minus f of b. So that's just the opposite of this, right? So this is the negative of f of b minus f of a. Not enough room on the page. All right, so if the definite integral from a to b is given as k, then swapping the bounds of integration is just going to make our answer negative k. And they say here that given that b is less than a, this is the same thing they're looking at here. This is just equal to negative b over a of f of x dx. So if we switch the bounds of integration, we're just going to make the thing negative. The next rule is talking about if we've got a function that's multiplied by some constant real number. And so what this means, we saw an example of this a few videos ago, and this just means we can pull this constant out. We can take the definite integral of f of x and then multiply that by k. So any definite integral, any constant we can pull out of that definite integral, f of x dx. All right. Another rule here is talking about if we're adding or subtracting functions and then taking the definite integral of that sum or difference. Can you imagine how we can simplify this expression? Well, we can simplify this by just taking the definite integral of each of the two pieces, dx, and then either adding or subtracting them. Okay? So this is kind of telling us that integrals work kind of the same way derivatives did, that we can pull out constant multipliers and we can separate addition and subtraction. The last two rules here are kind of interesting. So remember that an even function is a function that is symmetric about the y-axis. So it's the same thing on the left and right-hand side. So let me draw myself, here's my negative a, and here's my a. And so this definite integral is talking about this area here. Can you think about how I can simplify this integral a little bit? Well, these two areas are going to be the same because they're reflected about the y-axis. So this is just saying that we can double the integral from 0 to a of f of x dx, because f of x is an even function. Remember, even function, symmetric about the y-axis. And an odd function is symmetric about the origin. All right, so we've got the same look of the graph here in the first quadrant as we do in the third quadrant. So once again, if we wanted to calculate an integral from negative a to a of this, how do you think we could simplify this? Well, this looks like some of the examples we saw in the last module, where we've got the same area above and below the x-axis, so they're going to cancel each other out. Whenever you've got an odd function, you've got an integral, a definite integral equal to 0, as long as you've got the positive and negative bounds of that integral being the same thing. I want to add in a ninth rule, so give yourself a little bit of room down here. Because this is something that will help you out, and it's maybe something that you haven't thought about, but it's kind of nice to see. Let's say that we want to take the definite integral from a to b of some constant k dx. All right, so here's my k, and I want to take the area of that, the integral of that, from a to b. So what is the area of that rectangle there? Well, the height of the rectangle is k, and the width of the rectangle is b minus a. So this is just a really easy way to find the integral of a constant with respect to x. Okay, so I think that's important enough. It comes up enough times that it's worth having that extra rule sitting there on your rule sheet. And so those are the basic definite properties that we're going to use that are going to help us, as we're kind of calculating simple integrals in terms of other simple integrals over the next couple pages. And as I say, these rules you are going to see here in the integration properties. So these are common rules that you should probably have committed to memory in some form or other.